Welcome to this explainer. We use these incredibly powerful AI chatbots every single day, and honestly, sometimes it just feels like pure magic, right? Well, today, we're going to actually pull back the curtain and unveil that magic trick. We're diving deep into the exact learning paradigms that completely transformed artificial intelligence. And we're going to focus heavily on this revolutionary concept called self-supervised learning. Okay, let's dive into this. Here's how we're going to break this down. First up, how machines learn. Second, the self-supervised revolution. Third, predicting the unseen. And finally, we'll wrap up with the generative AI recipe. All right, kicking things off with section 1, how machines learn. Let's establish the baseline. So before today's AI models were out here writing code or drafting essays, we basically relied on two main ways to teach machines. On one hand, you've got supervised learning. This was the traditional workhorse for a long time. It uses pairs of input data and output labels to train a model. But here's the massive bottleneck with that. Those labels? They usually have to be manually annotated by human beings. Imagine paying an army of people to sit there and manually tag thousands of pictures of cats and dogs. It's incredibly time-consuming and, frankly, super expensive. Then, on the other hand, we have unsupervised learning. Now, this method uses absolutely no output labels. Instead, it looks at the raw data and just tries to discover inherent trends, like, say, clustering similar data points together all on its own. It's definitely more efficient because it doesn't need humans in the loop, but historically, it was pretty limited in what highly specific complex tasks it could actually pull off compared to those supervised methods. Which brings us to section 2, the self-supervised revolution, the paradigm shift. To really grasp what triggered this massive AI boom, let's look at how researchers define it. Quote, self-supervised learning obtains supervisory signals from the data itself. The general technique is to predict any unobserved or hidden part. End quote. And I absolutely love this last line. Self-supervised learning, the dark matter of intelligence. Think about that. It's this invisible underlying force. This paradigm perfectly bridges the gap between the previous two we just talked about, tapping into the underlying structure of the data without needing that massive army of human labelers. It is literally the hidden mass holding the entire modern AI universe together. So, the absolutely crucial point here is how we practically define this dark matter. Self-supervised learning, or SSL, involves training a model over pairs of input data and output labels, which sounds a lot like regular supervised learning, right? But here is the absolute game changer. The labels are naturally present in the raw data itself. That means no manual human annotation is required, zero. The model actually finds its own ground truth labels, hidden right there within the raw, unlabeled data. It's essentially creating its own answer key just by looking at the structure of what it's already analyzing. Moving right along to section 3, predicting the unseen, training tasks in practice. Now, this brings us to a massive, million-dollar question. If we really don't need human labelers anymore, how do we train models on massive amounts of raw, unlabeled text? I mean, we're talking about scraping the entire readable internet. How on earth does a machine learn anything deeply useful from just staring at billions of unannotated web pages? Well, one of the first major techniques is called the Cloze Task, or, if you want to be technical, the Masked Language Modeling Objective. You can think of this as a super complex, high-speed game of fill-in-the-blank. Here's how it works. First, the model takes a sequence of textual tokens, basically just a sentence. Then, it intentionally masks out, or hides, roughly 10% of those tokens using a special mask placeholder. Now the model's entire job is to predict what those hidden tokens actually are. And because the original word was right there in the raw text to begin with, the model can instantly check if its prediction was right or wrong, no human needed. This exact setup was used to pre-train incredibly powerful legacy models like BERT and T5. By just predicting that 10% of tokens we intentionally hid, the model naturally figures out the complex grammar, facts, and structure of human language. Now, what's really interesting is that this next method is the true, undisputed workhorse of modern generative AI. It's called next token prediction. This right here is exactly what powers modern giants like ChatGPT and Palm. The developers download huge chunks of raw text from the internet, sample a sequence, and then they train the language model to predict the very next token, given all the preceding tokens as input. Oh, and a key detail to remember, this happens in parallel for all tokens in the sequence. It is, for all intents and purposes, the ultimate autocomplete. Just by repeatedly trying to guess the next word across billions of sentences and checking itself against the raw data, the model absorbs an unbelievable amount of knowledge. This pre-training via next token prediction, it's basically the universal standard for generative language models today. All right, let's bring it all together in section 4, the generative AI recipe, baking the model. So if you wanted to build a generative language model from scratch, you basically need 3 essential ingredients. This is our generative framework. Step 1 is the transformer architecture. That's your physical neural network foundation. Step 2 is language model pre-training. This is the initial heavy lifting phase where the model actually gains its raw intelligence. And finally, step 3 is the alignment process. That's where we explicitly teach the large language model, or LLM, how to actually behave in a way that's useful to us. Let's break these down one by one. First up, let's look at the structural oven where this AI is baked, the transformer architecture. Specifically, recent generative LLMs use what's called a decoder-only variant of this architecture. Basically, it takes a sequence of tokens, which have been embedded into mathematical vector representations, and it transforms them. It does this using highly complex mathematical mechanisms called mask self-attention and feed-forward transformations. Now, if that sounds like a lot of jargon, don't sweat it. In simple terms, this network is specifically designed to let the model look at the context of a whole sequence and map out exactly how every single word relates to every other word. Okay, let's move on and see how this builds our model's actual intelligence. This is the pre-training iteration loop. It leverages that next token prediction or standard language modeling objective that we talked about just a minute ago. It's a continuous, highly repetitive cycle. Step 1, sample a sequence of raw text from a massive curated corpus. Step 2, pass that textual sequence right through the decoder-only transformer we just looked at. And step 3, train the model to accurately predict the next token at each position within that sequence. By just iterating through this loop billions of times over massive data sets, the AI gains its vast, raw understanding of the world. It's kind of mind-blowing when you think about it. But here's the catch. Having all that raw intelligence just isn't enough for everyday consumer use. After pre-training, the LLM is great at predicting the next token. But if you look at its raw output, it's often super repetitive and, honestly, kind of uninteresting. That brings us to our final ingredient, the alignment process. We have to define specific alignment criteria to fine-tune the model. We use techniques like SFT, which stands for Supervised Fine-Tuning, and RLHF, or Reinforcement Learning from Human Feedback. This absolutely crucial step is what takes that raw statistical output and transforms it into the helpful, harmless, and human-aligned text that you actually experience when you're chatting with an AI. It essentially bridges the gap between a pure prediction engine and a truly safe, useful assistant. So let's wrap this up with a pretty provocative thought based on everything we've unpacked today. If AI can teach itself the vast complexities of human language, reasoning, and logic simply by continually predicting the hidden parts of our raw data, what patterns is it going to uncover next? As this dark matter of intelligence continues to evolve and scale up, the possibilities for what these self-supervised models can learn about our world, our biology, and even our universe are truly limitless. Thank you so much for joining me on this explainer. I really hope this helps solidify these concepts for you. Keep asking great questions, and as always, keep learning.